So I actually have a lot of experience doing these band approaches to twisted bilayer graphene, twisted TMDCs. I won't be talking about that today. I'm going to sort of give an alternate approach to these 2D systems, and I'll try to motivate that very briefly. So I swear I didn't steal any of Alan McDonald's slides. I think he starts the same way at the beginning. There's basically two types of traditional moiré systems. You have semi-metals like graphene, and you have semiconductors like the TMDCs. And when you have a moiré pattern, you introduce some sort of long wavelength potential to these structures, and they start to couple in interesting ways. Now, band approaches are really good at dealing with these two class of problems, and right now this has been the main focus of experiments because these systems are the ones you want to do transport on. And that's where we see superconductivity and stuff like this. But let's say I wanted to look at a metal. So this is a type binding calculation in the metallic bands of a TMDC. As you can see, it is very hard to interpret anything useful from this. Maybe there are some tricks with some sort of projectors where you could start to extract some sort of flat bands, but I don't find this to be a very good way of doing science. So the problem is basically outside of these band edge phenomenons or semi-metal phenomena, we might need a different approach for solving these moiré systems. So what I'm going to do is focus on local density of states. So instead of thinking about K projected energy, I'm going to look at spatially projected energy. Okay. So to do that, we're going to start with a one-dimensional model. This is sort of a very traditional incommensurate chain model. I think it's been studied in a few other contexts. We have two layers here. We have a blue layer and a red layer. And I'm going to introduce a moiré pattern by changing the length scale of the lattice parameter in the red layer by a little bit. So one thing I want to mention here is that in 2D materials, you actually have three ways of introducing a moiré pattern. You can introduce a rotation, a lattice mismatch, or a strain that's anisotropic. And in 1D, you don't have this luxury. You can only do lattice mismatch. So I'm still going to call the lattice mismatch with this capital theta, just to make it connected to these twisted systems. And all it's doing is very slightly changing the length scale. And in particular, when theta is equal to 0, we have an aligned system, which is consistent with our understanding of twisted graphene. Okay. My interlayer coupling is going to be a variable in the model. Here I have a microscopic detail on the right. And what it's showing is basically the coupling between the layers as a function of the in-plane displacement between the two orbitals. And so you can change the strength of the coupling with this variable T1. You can also change the range of the coupling with this variable chi. Not sure about the Greek alphabet, might have got that wrong. Okay, so here are some density of states calculations. I want to focus first on the panel all the way on the left. This panel is showing two things. It is showing basically a conventional density of states for a 1D model near the center of the energy spectrum. We have just a nice, clean, uniform density of states. And then on the edges, you see these sort of Tootsie Roll or bow tie shaped structures. And these bow tie shaped structures are actually due to the interlayer coupling. So when the layers are aligned, you have a very strong interlayer coupling. This means that the two layers are hybridizing and you're getting two copies of the monolayer band structure, basically a bonding and anti-bonding copy. And as you move to intermediate alignment, halfway between, say, AA alignment and AA alignment, you're going to see very weak interlayer coupling. Now the next two panels on this left slide are increasing the moiré, or changing the moiré pattern. So on the left side, we have no moiré pattern. These are basically aligned systems, and I'm simply, shifting the whole system back and forth. Here what's going on is I've introduced a moiré pattern that has a very long length scale, and I'm locally computing the density of states at different atoms along that chain. Or in a more accurate description, I'm actually just shifting the two layers at the center and projecting to the center orbital. These are kind of equivalent sort of calculations. Now we can see two sort of phenomena happening. Near the low energy, we see nothing changes, so we still have conventional 1D block waves. But on the boundaries of our energies, we're seeing these very bright lines, which are localized in space and also separated in energy. And this is just a real space representation of the moiré flat bands. So if we remember the flat bands in graphene, they show up as these bright spots on the AA locations. And so if you took some sort of line cut through the AA spots, you'd see something exactly like this as a function of energy in space. Okay, on the right here, I've increased the interlayer coupling by a factor of 3. We see much of the same physics at high energies. You see these moiré flat bands. This is the intersection of two parabolic bands. But we see in the metallic spectrum, we're getting something very different. And this is really, it looks at first glance very similar. You have these bright spots, you have these energy separations and spatial confinements, but it's really different because they're not flat bands. They're not these separated, nice discrete energy levels, they're actually continuous. And they depend very sharply on the local stacking between the layers.
So T1 is the interlayer hopping.
Yeah, T1 is the interlayer hopping, and T0 is the in-plane hopping, which in some other slides will just be set equal to 1 as the energy scale for the system. Yeah. Okay. So this was just changing the interlayer strength. Now I'm going to also change the interlayer strength, but now make the interlayer coupling longer range. So I'm going to change that Greek variable. I don't trust my knowledge of the alphabet.
But I hope you trust Greek.
I do trust Greek. Well, I better, because he's my Greece is my advisor, right? Tim Cook.
Depends on the gifts.
I don't know what gifts I take.
So here now we've increased the sort of coupling length, and this has two effects. One is it increases the average interlayer coupling strength, so we can see the sort of bonding anti-bonding separation is larger, but it has the negative effect of making the spatial dependence of the moiré potential really weak. So you can see in this panel all the way on the left, if you look at this highest energy density of states calculation, it has almost no spatial variation, and that's because the long length of the interlayer coupling is basically averaging over multiple sites, and so it can't really see the spatial variation in the moiré lattice. So if you want to see flat bands, that's not very good. However, these calculations do some interesting things, and this is where I start to say that this interpretation of the twistronic features is somehow more natural than the band structure interpretation. If we look over here, we can see this nice sharp V. So I just want to ignore all the details and just say, okay, this is some sort of confining moiré well. I don't care about how it was generated. And if we assume this is some sort of potential well, when you actually create a moiré pattern, it's going to be able to confine electrons. And so we can kind of see these energy levels that are separated pretty clearly, and they also have a different number of nodes. So in 1D, this corresponds to sort of higher angular momentum, or I guess in this case, linear momentum. So we have these sort of confined modes down here. We have some sort of weird V-shaped potential confining modes up here. So let's see if we can actually validate this. So I'm going to treat this like a harmonic oscillator and basically extract all the relevant parameters from the microscopic model. And then we're going to see if that fits well with the calculations we did. Okay, so the first thing you need for a harmonic oscillator is an effective curvature or an effective mass in momentum space. So I take my 1D model. It's a cosine band structure. You can very easily extract what m star should be. And then you can also extract the spatial dependence of the interlayer coupling. And here it depends on the parameter d, which is the configuration between layers. If you want to turn that into a real space potential, you have to multiply by the moiré length. So that'll be done later. But again, this potential is a very simple exponential form, and so it's very simple to extract some sort of effective quadratic term near Hamiltonian. Okay, so here is the explicit sort of low energy expansion we want to do. We have a quadratic monolayer Hamiltonian for layer 1 and layer 2, and then we have an interlayer coupling, which sort of mixes layer 1 and layer 2. I don't want to mix layer 1 and layer 2 because I'm really bad at quantum mechanics, and I don't know how to do a two-dimensional Hamiltonian, so I really want to make this one-dimensional. So the way you do that is you introduce this sort of bonding anti-bonding idea that we talked about earlier. So you just do this 45-degree rotation, and you can explicitly separate this Hamiltonian into a bonding and anti-bonding that they're completely diagonal. They don't talk to each other. And now we see we have a harmonic oscillator expansion. We can write it explicitly as a harmonic oscillator and extract what the effective frequency is. So if you're familiar with the semiconductor moiré potentials, this is not so surprising. Basically, the details of the microscopic model tell you what the effective frequency is, and that frequency depends on the length scale, which is indicated by theta. So as you make theta larger, you're making the moiré length smaller. And if you have a more confined, a smaller potential, it has a sharper curvature. And so that's why the frequency of the harmonic oscillator grows with the twisting angle. As the pattern gets smaller, the states are further apart because you have a sharper well. Okay, so this agrees really well with numerical calculations of the simple model. So this middle panel here is showing the total density of states as a function of theta. So we're going from aligned systems to about 0.4, which is a moiré pattern of about 2 lattice lengths. Now, if you look at this, and I didn't tell you what the topic was, you'd say I was doing a Hofstadter butterfly or quantum Hall effect problem. So you can see the patterns here. You have these competing length scales. It's going to give you these fractal patterns. I zoom up here on the high energy mode at low twist angles, and I then basically put in the formula for this omega theta depending on theta, and I do 1/2 of h bar omega, 3/2 let's see, 1/2 h bar omega plus 0, 1/2 h bar omega plus 1, 1/2 h bar omega plus 3, etc. And if you do that, you can basically see that the harmonic oscillator levels, like in this diagram, exactly match, at least at small angles, with the observed flat bands. Okay. So this is basically telling us that, indeed, when you have this sort of band edge effect, you can model it as just an electron gas in a confining well, which is maybe not that surprising. Okay, so I'm going to go back to this oscillator equation and sort of unpack it in a different way. So again, we said there was a quadratic term in the kinetic energy, a quadratic term in the potential energy. So let's explicitly do that. First, I'm going to change the dependence on R to a dependence on configuration. As I said before, that introduces a factor of theta. And when you do this, you can rewrite this harmonic oscillator frequency in terms of this very symmetric formula. So we basically have the curvature of the monolayer band times the curvature of the real space potential. This gives you the effective frequency of your moiré harmonic oscillator. Okay, so I'm going to look at this and make an argument about why the harmonic oscillator states don't exist through the entire material. Well, it's pretty simple. When this term over here becomes very small or disappears, you no longer really have any sort of confining well. So if we look at, say, this energy scale right here, all the way over to the left for the aligned system, you see there's no dependence on the stacking. This means that the block waves there do not see any sort of external potential due to the moiré pattern. And so when you twist the system, you don't see very much confinement. They basically still look like block waves. Okay, so again, this term over here has sort of disappeared in our effective model, and that means we no longer have these nice flat bands. Okay, so inspired by sort of this equation, I'm going to talk about this configuration momentum duality. So, sorry, this is the equation I'm talking about. You know, if I just ignored E and T and just replaced D and K, you can kind of interchange these variables and nothing really changes. And I'm going to argue that these are actually the same object, just in different bases. Okay. So what have we been looking at? We've been looking at the local density of states as a function of configuration. So what I did was I basically averaged over all the block waves for a given configuration, and I computed the local density of states at that configuration. Well, let's do the duality. Let's swap the variables. Okay. And now I'm going to get a momentum projected density of states. This is projecting onto the monolayer block waves. But I have to integrate over all the configurations. Now this is a construction I haven't ever seen presented in any of the studies on moiré systems, but I argue that this is a very, very useful quantity to figure out. So this is basically saying for a given block wave, I want to know what its dispersion is due to the interlayer coupling. It's kind of like saying I have a well-described eigenvalue in the monolayer. Because the interlayer coupling depends on space, I want to see how much that block wave gets perturbed over the entire system. So here I have this plot from earlier, and I've now done the exact same system, but I've computed it in the momentum basis instead. And so we can see, if I didn't tell you that this was done in real space and this was done in momentum space, they're almost indistinguishable at high energies. So you're seeing that the moiré flat bands are not only confined in real space, they're also confined in a projected sort of band unfolded description of momentum space. Again, maybe not that surprising. What is interesting, though, is if you look now at where this thing failed to have confined modes, we see that the momentum projection just shows these nice, clean bands. So basically, you have returned to a conventional band theory. You have states that are highly localized in momentum and highly localized in energy, and they depend smoothly on the k variable. So what if we broke our harmonic oscillator approximation by breaking the other variable, right? So we know that if you don't have a strong moiré potential, you go back to block states. What happens if you don't have a strong effective mass? You have effectively some sort of very flat band in the monolayer, or you have some very strong interlayer coupling in the bilayer. Okay, so this is going to be a little bit hand-wavy, but I just want to show the picture because I think it's pretty convincing once you see the whole argument. If you think about the monolayer coupling being very, very strong, so here HI is the monolayer Hamiltonian, T is the interlayer Hamiltonian, you can have this sort of moiré crystal or just a conventional crystal where you have couplings along a single layer and almost no interlayer coupling. And if you do a density of states calculation on these sort of systems, this is the pattern you see. This is in configuration space, this is in momentum space. We see a continuous band, that's conventional, and we see a continuous band in K space, again, conventional. Now, if I think of the other limit, where the monolayer coupling basically disappears, so this can be done by either having a flat band in the system or by having a very strong interlayer coupling, now I have what I call still a crystal, but it's a crystal in the momentum space. And so if you're really familiar with these K.P expansions, this is basically the statement that what if your K.P expansion did not depend on the diagonal components and only depended on the scattering elements in this expansion? Well, I'm saying that there's a momentum configuration duality, so I hope these figures swap, and indeed they do. So what's happened here is now, because the interlayer coupling is so strong, your bands are not well defined. They're very spread out, because as you move across the surface of the moiré pattern, you're going to see a lot of different stacking arrangements, a lot of different interlayer couplings. And in real space, because the in-plane coupling is effectively 0, all you're seeing is basically the splitting due to the interlayer coupling between the layers. So it kind of looks like you have bands in the configuration space and you have a continuum in the block basis. So the reason this seems kind of silly, right? Because this is just basically dimers, right? They're molecular dimers that kind of vary in space. It maybe doesn't seem very interesting, but it has a really important interpretation when you look at these twisted systems, because in certain choices of the variables, you can actually have both of these situations occurring in the same material, which I think is very interesting. So up here I have what I call the moiré molecule. These are the harmonic flat bands due to the confined potential well. And I have two types of crystals occurring in the metallic bands. So over here I have a conventional crystal. I have bands in K, continuum in D. But at slightly lower energies, I have bands in D and continuum in K. So I think this is a really pretty way of looking at the twisted materials. I hope that it maybe gives some insight into, if not the flat bands, it gives some insight into sort of the underlying structure of this Hamiltonian. And I just want to quickly describe how this momentum crystal that I called actually is realized in an actual system. So this calculation was for not real space. It was in the configuration space. So what you have to do is unfold this system into real space. So the way you do that, if you have a commensurate system, is pretty easy. You just start at your initial alignment, and then you just sample in an even way until you return to where you started, right? Because maybe in this case, there's 10 unit cells in the moiré pattern. So I call this a moiré comb. You sort of just put this little ruler there, and you count out the states. What you see is that at low energies, we have, again, these bright spots which correspond to the moiré flat bands. This is the moiré length. It's very small in this plot. However, at the intermediate energies, we can see different sorts of patterns. Now, taken in isolation, I would say this state and this state look very similar. But what happens is when you do a slight change in the local stacking between the layers, this is a change that is smaller than the actual inverse moiré length. You see that this low energy structure completely changes. And so while these states are very stable under small changes in the atomic geometry, this thing is extremely unstable under small changes in the atomic geometry. So it's going to be really hard to see maybe an experiment. But if you have an incommensurate system, here I'm just basically making it slightly incommensurate by adding a small delta to my commensurate theta. We now see that these isolated states depend smoothly on configuration and energy. And so they're sort of these like localized modes that are banding up and down. It's quite cool. This whole interpretation has a very deep connection to some studies in the 80s and the 90s on 1D type binding Hamiltonians and incommensurate potentials. I'm not going to talk about that, but if anyone's interested, you can ask me later. It's a different way of arriving at something that's kind of already understood for a one-dimensional non-bilayer Hamiltonian. Okay. So in my last few minutes, I'm going to go over some 2D examples. Okay, bilayer graphene. Hopefully everyone understands this from the last two talks. You have Dirac cones. If we look at the spatial dependence of the density of states, you also have Dirac cones, which I think is kind of cute, but these are not the momentum Dirac cones. These are basically telling you that as you move away from AA stacking, the interlayer coupling is changing, and so you're getting different bifurcation of the low energy modes. So in particular, if I was to take a density of states, a density of states plot right through here, you're going to see the traditional AA feature, which is, I think, basically a Dirac cone with a constant background. But if you do the cut through AB or BA, you're going to see the parabolic features of the parabolic touching point. So it basically goes to 0 in a different way. Now, if we do this calculation with this large system and we twist it, we can see these bright spots at low energy. Okay, this is maybe not the best way of doing magic angle physics. I'm not able to extract a lot of useful information. I have energy resolution limitations due to the matrix of the method of my matrix calculation. So let's look at a different part of the spectrum. So now I'm going to be looking at these high energy regions. This is basically a Lifshitz transition in the monolayer band structure. You're going from a negatively curved surface to a positively curved surface. And so for those of you familiar with graphene type binding calculations, these cause very large peaks in the density of states. And because there's one from each layer, they can basically split each other by the interlayer coupling. So now the splitting of these peaks depends on the stacking. And so again, you get these nice, pretty sort of confining wells. And unsurprisingly, if we introduce a twisting angle, we're able to cause localization because of this moiré potential. So this is, I think, an interesting phenomenon that I haven't seen reported anywhere. We've sort of been aware of it for about a year. I haven't been able to convince anyone to do an experiment on this. But I think you could optically access these states. These are really, really confined. They have hopefully some useful matrix elements in them. The symmetry of it, it's not really clear to me yet. I'd have to do some additional thinking about that. But you can see all of these nice, small, localized modes. These are basically different flat bands with different harmonic or angular symmetry. And we'll see that in the next few slides. OK, so I'm going to now look at the 2D TMDC, bilayer MOS2. In this model, we only have coupling between the chalcogenide atoms in the center. This band structure plot over here is in two colors. There's an orange band and then black bands. The orange band is the bands of the monolayer. The black bands are the bands of the bilayer. We can see that they're split because of the interlayer coupling. What we're going to do is look at different regions of this in real space and see if we can make sense of it. OK. So this is the band edge. This method is not very good for this. It doesn't have enough energy resolution. So instead, we're going to use type binding calculations. And we can already see something very suspicious. We see that the flat bands are separated in kind of equal spacing, and that the size between, say, the Fermi energy of the original bilayer and the twisted bilayer, it scales linearly with the twisting angle. So this is, again, consistent with a harmonic oscillator. And so I did a number of these calculations. I extracted the band average value. That's on the left axis. I extracted, of course, the twisting angle. That's on the bottom axis. And also the bandwidth, which is the color. So we can see that as the twist angle gets small, you have these bands that are becoming closer and closer to the Fermi energy of the untwisted bilayer. And their width is getting smaller and smaller. So this is the moiré continuum that's been sort of talked about for the parabolic systems. OK. Let's look at two nice pictures now. Here I am in this sort of metallic region in the center of the TMDC valence band. We can see that the untwisted density of states is very interesting. And when you twist it, you're able to, again, get these sort of localized modes. And there's a little bit of very thin line showing up here, which might be this momentum crystal that I talked about. This is actually much clearer at lower energies. So this is a really interesting result. We have, if you look at the untwisted configuration on the bottom left here, you have multiple potential wells that are of different shapes and at different locations. There's a few at the AA stacking, one at the AB stacking. When you twist the system, you get multiple moiré flat bands, all at different locations in space and with different harmonic frequencies. And on top of that, you can see some actually pretty clear momentum crystal behavior over here, although it might not come out well on the slides. Sorry about that. And just to wrap it up, the reason why we did this is because here's the band structure. So this is the band structure for that region. I think you might, like I said, you can kind of see a flat band here and a flat band here, which correspond to these bright spots that have the arrows on them. But I just think that looking at just the density is a much more natural way of dealing with this problem. And just for fun, I also did some 2D density calculations. So these are line cuts along the diagonal of the moiré supercell. This is what they actually look like in 2D, in real space. So we see the lowest mode is indeed an S wave, similar to graphene. It's just a bright circle. The next mode is this sort of P wave. It has non-zero angular momentum. If we go up a little bit higher in energy, I think we actually have a coexistence of two different moiré bands. We have this sort of bright donut, which is even higher angular momentum, kind of like a D wave in 2D. And we have this additional bright spot, which is like an S wave of a different moiré pattern. And here's my summary slide. And here are my acknowledgements. Thank you. Sorry for running a little bit over.